All right, so today we are moving on to magnetic force. And so the last lesson we learned about how when there is a wire and it has electricity moving through it, there's a magnetic field around that wire. And so now we gotta think, if there's a magnetic field around a wire and so what we talked about is if we put a magnet there, then it's going to move. It's going to point in a specific direction. Using our right hand rule, we can predict what direction it's going to go in, right? And so you've done a bunch of questions already, like if there is a wire with a current going up, current is I, then the magnetic field, you use your right hand, you can see that it's going to go into the page on this side and out of the page on this side, and we can predict where a compass is going to point. But if there's a compass pointing that way, that means there's a magnetic field, which means if we would put a magnet here, right? A magnet, it's going to feel a force. It's going to either be attracted or repelled by this not imaginary magnetic field, but this new and induced. We call it, the word is induced magnetic field because it's like created. And so what we're going to talk about today is there is a magnetic field produced and it's got force. Okay, there's a magnetic force that comes along when we put current through a cord, and we can calculate it. And so this was in the 19th century, a scientist named André Marie Ampère was studying the magnetic effects of an electromagnet. This is a produced magnet through electricity, right? And demonstrated the forces that a current-carrying wire have on each other. And so what he did is he was able to measure this by laying wires beside each other, by using known magnets to pull wires that had known amounts of current going through them. And so we need to know a few things. Current is the letter I. We know this already. I for current. I don't know why. Is measured in the amount of amps, which is the amount of charge. That is passing through a wire at a given amount of time. 1 amp is 1 coulomb. Remember, this is 6.25 times 10 to the 18 ECs, elementary charges, right? This is what we learned earlier in electric fields, in that this means there's this many electrons passing in 1 second. 1 second, okay? So that is 1 amp. This many electrons, 6.25 times 10 to the 18 electrons passing in 1 second. That is current. And so if there's 2 amps, there's double that many electrons passing each second. But it's easier just to say 1 amp. Magnetic field, okay? Here's the new letter, B. Because. So the magnetic field B is the area around a magnet where another magnet or current-carrying wire will experience a force. So this is the big idea of today's lesson. A current-carrying wire is going to experience a force when it's in a magnetic field, which means it's by another magnet. And so if it's by another magnet, it's in its field, right? So the magnetic field just means you're close to it, right? So if you're close to a magnet, you're in its magnetic field, you'll feel a force. So magnetic field strength. Okay, this is the field strength. How strong is the field that we're in? Okay, is measured in Teslas. Now I thought Tesla, that's an electric car. Isn't a Tesla going to be more linked with electricity? Well, yes, but we can create magnets, a magnetic field with electricity. So, and this was Tesla's big thing, is that he found the link between magnetism and electricity. Specifically, he didn't find the link, but he found how to utilize that link to produce electricity. We'll talk about that more in grade 12. 1 Tesla is 1 Newton per amp meter. Okay, and this is really cool. What this means is, for every amp of current that passes through a meter of wire, we experience 1 Newton of force. Okay? And so if we could break down these units, but essentially what it means is for every, remember this is amp is a coulomb per second, okay, and that's a meter. So for every coulomb, that's 6.25 times 10 to the 18 electrons that pass in a second across a meter of wire, we're going to feel 1 Newton of force. That's if there's 1 Tesla. So that's the basic. You could break this down, and this is a huge unit, okay? And so instead of writing all of this stuff, we just write 1 Tesla, okay? And so what it means is if there's current in a wire going across a length of wire, there's a force, and that is a Tesla. The force that 1 amp would feel across a meter of wire. All right? Pretty crazy stuff. Here is the formula that we're going to use that was found. All right, and it goes like this. F B equals B I L. All right, there it is. F Bill. Great formula. FB stands for magnetic force. So that is the force felt, and that's of course in newtons. Always forces in newtons. That's the force felt by the wire. Okay. B stands for the strength of the magnetic field. Okay, and this is in, like we just said, Teslas. Okay, and we've talked about the other ones. I is current. That's measured in amps. And last one, L, is length. How long is this wire? And so that's in meters, length of the wire. Quick example of how we can use this formula. Okay, we've got here a 1.55 meter long wire. Okay, so that's length is 1.55 meters. Okay, as carrying a current that's I of 5.00 amps, okay, through a magnetic field. Okay, the force on the wire is, so we know FB, that's the force, and that is 0.375 newtons. What is the strength of the magnetic field? So we're looking for big B. Now these all have arrows, so these are vectors, but we're not given any directions because you don't know how to find that yet. We're going to do that real soon. Okay, but we usually will need a direction. So we use our formula, FB equals BIL. My big hint to you, anytime that you see a wire in a field, you see magnetic field, we need B. We only have one formula. It's really nice, okay? And so you're going to be using this. FB equals BIL. If you see magnetic field and you need a calculation, you're doing this one. So it's not too crazy. So what we got is 0.375 equals B times 5 times 1.55, and we get our answer of B equals, that'd be 0.375 divided by 5 times 1.55. Looks good to me. We got 0.0484 Teslas is our unit because it's a magnetic field. So that's our first time using Teslas. Looks good. Alright? And so, here's how we find direction. Because it's not straightforward. How do we know what direction this thing is going to feel a force? So this is a wire. All this is, I'd be doing a demo now. I'd be holding a wire out, okay, and then holding a magnet close to the wire. Okay, it's going to feel a force if there's a current going through it, okay? And it's going to then probably move in that direction if there isn't enough friction to stop it, okay? Here's how we determine the direction. Right hand rule number 3. Guess what hand you use for this? Not your left hand, your right hand. If you use your left hand, you'll do it wrong, okay? Here's the rule, okay? Your thumb is the current now. Your hand is open. Your palm, it's like you're slapping someone, okay? When you slap someone, okay, go find your little sibling or something. Kyra, I know you got a little, no, I'm just kidding. When you're slapping someone, the force comes out of your palm, okay? And so, out your palm is the force, your fingers, all your fingers represent the magnetic field. The way I think of this is the field is large. Okay, it's not just one thing. Generally, the current is going through a straight wire. So this is a straight wire, not a coiled wire. Okay, this is a straight wire lying in a large magnetic field. So there's many fingers showing the field going out. The palm is the force that you're slapping with, and your thumb is the current of the single wire going through the magnetic field. And notice your thumb. It is perpendicular to the magnetic field. You cannot have your thumb in line with the magnetic field. If it is in line, we will find out later that there's no force then. It has to be perpendicular. So get your hand stretched out like that, like it is shown in the picture. Your thumb has to be perpendicular to the magnetic field. And then the force will come in the third dimension, out. Okay, so this is a three-dimensional drawing. It's tough to do that, okay? But use your hand. So, let's check this out. What does this mean? If we've got... Well, here's an example. Let's use the following diagram to determine the direction of the current flowing through the wire. We know that if this is a magnet, this is north, this is south, north, south, this is north, south, then the direction of the magnetic field between these two poles is going out of north towards south. So the magnetic field, that's B, is across there. Okay? What else do we know? We know that the force here is into the page. Okay? So we've got the force is into the page. And so we set up our hand so that our force, that's our palm, palm is into the page, and we set it up so that the magnetic field, that's our fingers, are going to the left. Okay, and now we are looking for the direction of the current, so we're looking for what direction is our thumb going. So set up your hand so your palm is into the page, and your fingers are to the left, and your thumb is left with no option but to point what direction? Down. Down is the answer, okay? Thumb, which is the current. So that's our answer. So these are so much fun. I love these questions. And it actually works this way. And this is what electricians are doing all the time, okay? So another question. What's the direction of the force on a wire if the current flows east and the magnetic field is directed up? So what do we got? We got current going east, that's this way, so that's I, okay? And we've got a magnetic field that is directed up. Up is not north, okay? Up is another way of saying out of page. Okay, and so the magnetic field, one way of drawing this, what color did I do magnetic field up there? Red. Magnetic field is out of page. It's like this. We've got a whole bunch of circles here that are out of the page circles. Okay, and we got this current going through it, and so now we set up, right, and we look, magnetic field is fingers. So we got fingers, and in the purple we've got our thumb. And so we set it up so our fingers are going out of the page and our thumb is going east. And where is our palm facing now? That's our force. We're looking for the force, so we're looking for our palm. And it is facing down again. And that's our answer. The answer is down, okay? What is the direction of the current flowing through a wire that would experience the force towards the east when the magnetic field is pointing down? Okay, so let's look at that again. This down means into page. So there's a large magnetic field that's into the page. So that's just circles with X's in them, right? That's into the page. And the magnetic field, the force towards the east. Okay? So the force towards the east means the force is this way. This is FB, is that way. And that's, once again, that is our palm is the force, magnetic field is into the page. So get your palm facing east, your fingers pointing into the page, and your thumb perpendicular to your fingers, and it is pointing down again. I should change these examples. It's always down. Don't the answer's not always down, okay? Don't get that from these examples. The answer's not always down, but it is this time, okay? But you can always set up your hand to see, okay, the force is out of your palm, your fingers are down into the page, and we've got the direction of down, okay? And so, last example, wire is 1.25 meters long. So this is going to look a little bit different because we're actually doing calculation. So we've got length equals 1.25 meters, and we've got a current, that's I, is 3.25 amps, and it's north. Oh boy, now we got directions. Can we put it all together? The current carrying wire is in a magnetic field, that's B, with a strength of 0.465 Teslas out of the page, up. Okay, so I'm doing that as out of the page. And guess what? I'm guessing, I'm just looking at BIL, I'm guessing we're going to find force. Well, let's look, what is the force exerted on the wire? No surprise there. So that's our question. Well, nicely it's set up. F equals BIL. So this is a nice one, we just plug it in. We've got B is 0.465, we've got I is 3.25, and we got L is 1.25. And we get the force in newtons is 0.465 times 3.25 times 1.25, and we get 1.89 newtons. And what is our direction? Okay, we should always have a direction, and now we know how to find it. So we've got to do some thinking. We've got I is north. Okay, so we've got a current. Purple, right? It's north. We've got a magnetic field into the page. X all around it, into the page. So our fingers go into the page, thumb that way, and where is your palm facing? Oh, did I say in? It's out of the page. Ay. Even in the video I can't get it right. It's right in front of me. Out of the page, current is up, and so you set your hand up and you should get that your magnetic field...
Daddy, lunch is ready.
Lunch is ready? Okay, thanks, man. Is this way.
But Mom told...
Your force is this way.
But Mom told me that it was lunchtime and I could go tell you.
Okay, that's good. So our answer is... I'm just recording a video. I'm almost done. Okay? East is our answer, and so all that work just for the direction, just to get a final answer. And we're done. I have to go. I'm in a bit of a rush. I got to go have lunch now. So, thanks for joining me. Have a good one.